Today, we're diving into the strange and honestly world-changing realm of quantum computing. And we're going to kick things off not with a computer, but with a simple trick of light that seems to completely break the rules of reality as we know them. So let me just ask you a question that sounds completely impossible. Can you take a setup that is blocking all light, add another blocker right in the middle, and suddenly have light pass through? I know, it sounds like total nonsense, but believe it or not, it's the key to unlocking the whole quantum world. And this isn't just some thought experiment. You can actually try this yourself at home with a few polarized lenses, like the ones from 3D movie glasses. It's a really simple setup, but the result is so surprising, it's the perfect way to introduce the bizarre rules that are really running our universe. Okay, let's walk through this. First, you take two polarized filters and you line them up. Light goes right through, no surprise there. Then you rotate one of them 90 degrees. And just like that, all the light is blocked. It's completely dark. So far, so good, right? This is all totally normal. But here is where the magic happens. We take a third filter and we slide it in between the other two, setting it at a 45-degree angle. And all of a sudden, light comes through again. I mean, think about that. We added another obstacle, and yet light found a way through. How on earth is this possible? Well, it's not a trick. It's a window into the quantum nature of reality. So, the bizarre result of our little filter trick is explained by a core principle of quantum mechanics called superposition. This whole idea first came to light in a famous experiment back in the 1920s that just completely shattered our classical view of how the world works. In what's called the Stern-Gerlach experiment, scientists fired silver atoms through a magnetic field. Now, classically, you'd expect these atoms, which act like tiny little magnets, to get deflected by different amounts, creating a continuous smear on a detector screen. But that is not what happened. Not even close. Instead, they found just two distinct dots. Every single atom was forced into one of two states. You could call them spin up or spin down. Nothing in between. And this illustrates the idea of superposition perfectly. Before an atom hits that magnet, it isn't spin up or spin down. No, it exists in a kind of probabilistic cloud of both states at the same time. It's the act of measuring it with the magnet that forces it to choose one of the two definite states. It's not that we just don't know its state, the state itself is fundamentally undecided until you measure it. And this is exactly why our filter trick works. So, how does this weird property of being in multiple states at once actually help us compute anything? Well, it lets us create a revolutionary new kind of information bit. A classical computer bit is super simple, right? It's either a 0 or a 1. It's on or it's off. But a quantum bit, or what we call a qubit, takes full advantage of superposition. It can be a 0, a 1, or a combination of both of them at the exact same time. And this means a single qubit can hold way, way more information than a classical bit ever could. And just like those silver atoms, this superposition only lasts as long as we aren't looking. The moment you try to measure a qubit, you force it to collapse into a definite 0 or 1, and you actually change its state in the process. This is both the source of a quantum computer's incredible power and, frankly, one of its biggest challenges.
Okay, so superposition is definitely weird, but there's a second quantum property that's maybe even stranger, and it's what really gives quantum computers their exponential power boost.
This idea was so unsettling that even Albert Einstein couldn't get on board. He famously called it spooky action at a distance, because it just seemed to violate the most fundamental speed limit in the universe, the speed of light. This spooky action is called entanglement, and what it means is you can link two qubits so they share a single quantum state. Their fates are intertwined. So if you measure one and find out it's a 0, you instantly know the other one is a 1, even if it's on the other side of the galaxy. It's not just that they're correlated. They are literally two parts of a single system linked instantaneously across any distance. So we've got superposition and we've got entanglement, two incredibly strange ideas from physics. But so what? Why does this matter? Well, harnessing these weird properties is what's about to launch the next great technological revolution. Because a quantum computer can explore a huge number of possibilities all at the same time thanks to superposition, and because its qubits can be so intricately linked through entanglement, it can tackle certain types of problems that are mathematically impossible for any classical computer to solve in any reasonable amount of time. So, what does this incredible power actually unlock in the real world? Well, for starters, there's a quantum recipe called Shor's algorithm that could factor massive numbers, which would basically break most of the encryption that protects all of our data online today. We could also simulate molecules with perfect accuracy to design brand new drugs and materials. And another tool, Grover's algorithm, could act like a quantum search engine, zipping through massive databases at unimaginable speeds. These aren't just small improvements. We're talking about complete game changers. And to put that encryption threat into perspective for a second, the security of your bank account, your emails, pretty much everything depends on a simple mathematical truth, that it's really, really hard to find the prime factors of a huge number. For a classical computer, it could take billions of years. For a powerful enough quantum computer, it could take just a few hours. This all leads to a pretty profound idea. What if computation isn't something we humans invented, but a fundamental property of physics itself? The universe is constantly performing these impossibly complex quantum calculations all around us. With these new machines, we aren't really building something new. We're finally learning to speak the native language of the cosmos. The only question is, are we ready for what it has to say?